Okay, let's approximate. Let's approximate the area under a curve using Riemann sums. Before we dive too deep into this, we need to review Riemann sums and what they are first. So I'm just going to go right here and we'll talk to you about a couple of things with this notation. This is the sigma notation, and what we do with this is a Riemann sum. We're going to add, it's telling us repeated addition, but the numbers are going to change that you're adding. So you start with this number. Oh, that was not supposed to make a circle. We start with this number, we end with this number. So I would start by plugging in a 1 into whatever function is here. And then I go to the next 2, go to the next 3, plug in a 4, plug in a 5, plug in a 6. And then the sigma notation means you're going to add them all up. So adding these all up would make 21. Okay, next we're going to go to this one. Here we're starting with 3. We're ending with 7. So we plug in a 3, a 4, a 5, a 6, and a 7. Give me a second. I'm going to just grab my calculator here. Feel free to do the same. You can pause the video to do that. 135. Okay. The next one here, they're kind of messing with us a little bit with the notation. N is an integer, but they're not telling us what it is. So just N is the number in mind. The number that's actually changing each time is what we have in the K spot. So we'll start with a 1 in the K spot. N, maybe it's a 7, maybe it's a 6, maybe it's a 5. They didn't tell us it's N throughout the whole thing. So it would be, the first one is 1 over N. I'm plugging in a 1 in the K spot. The next one is 1 over N, and I'm plugging a 2 into the K spot. The next one, 1 over N, and I'm plugging a 3 into the K spot. And this pattern continues until I get to the top, which was an N. So generically, that's what we'd be looking at. Okay, now the next, and I can't do anything more. I mean, I could factor out 1 over N, but other than that, I can't really do much with that. Let's go to the next one down. Now the next one, they have told us basically here, hey, it's a function, but you don't get to know which one it is. So maybe it's a K squared plus 1. Maybe it's a I squared. Maybe it's a, we don't know. So here's what we do know. We start at 1 in the I spot. So it's your function evaluated at your first x. Now this delta x, it's a constant. Again, we don't know what it is. It doesn't have an I in it. So it is what it is. Later on, if they tell us what it is, then we'll put it there. But right now we don't know. The next one is going to be the function evaluated at the second x. The next one is the function evaluated at the third x. And this pattern continues until we get to the nth x, plug that into the function, and then multiply it by that delta x again. Also here, I can't really do much. I could factor out whatever that delta x number is. They didn't tell me it, so this is as good as I can do for now. All right, properties with summations. You've already seen basic properties of summation in probably an Algebra 1 class. Like when you were doing sequences and series and stuff like that. So I'm not going to re-go over all of that. Also, back then, you were probably given these 3, but these are more advanced, so I thought I would remind you of these. If you had a summation and you just had the variable there, you could plug them all in, or you could use this formula. If I scroll back up here, I could have used that formula for this one. So if I chose to use the formula here, it is, remember, what was it again? Let's scroll down. N times N plus 1 over 2. N is a 6. n plus 1 is a 7 all over 2. Oh, hey, these will make a 3. We get 21. So same answer, just a shortcut. Okay. Now, notice that this started with 1, and these all start with 1. So this one right here, I can't use for B because this didn't start with a 1. However, I could have done it where J started with a 1, we did the 7. I could have used the formula for that because it started with a 1, but then I'm over counting. I don't want to include the 1. I don't want to include the 2. So I'd have to subtract when J was a 1 and a 2. And then I could do that, and I would get 135. So hopefully that rings a bell. It's kind of a blast from the past. And then likewise for the cubic. Okay? So let's practice a cubic. Since it starts at 1 here, we can use the cubic formula. So here it's find the sum of x cubed over the integers when x is 1 and stops at 10. Well, if I use that formula, n is 10, n plus 1 is 11 over 4. All right, so basically 100 times 121 over 4. I get 25 times 21, excuse me, 25 times 121, 3,025. Now, I could have done each one of the numbers and added them up, but if you had a lot of them, it would take a long time. Okay, the meat of this section is looking at the area under curves. Okay, I promise I'll tie this into summations here in a little bit. All right, so for this one, not wanting that. Okay, for this one, you can see that we have an area under a curve. Just slide that back over. Actually, I might be doing that. I'll just squeeze them both together closer. Okay, the one on the left is an under approximation. Some people say it's a lower approximation, okay? Because it's not going to be counting all these little areas that we have here. Those are left out. The one on the right here is either an above or an over approximation, okay? Now, let's keep moving here. If I'm going to approximate the area for each one of these, I am going to, let's see, how many rectangles do I have? I have 1, 2, 3, 4, 5. Each one of them has 5. And it looks like to me that the consistency here, change in x is 2/5, change in x is 2/5, 2/5, 2/5, 2/5. So it's the change everywhere. And actually, even on this one, it is also the change in x everywhere. Okay, it looks like I am going and I'm trying to approximate the area under this curve from 0 to, this is a 2, right? So I'm doing that span, which is 2 units, and I'm dividing it 2 units long, and I'm dividing it into 5 pieces. So 2/5 would be the equal, each rectangle of equal width. Little sidebar comment, when we cut into a bunch of rectangles with equal width, we call it a regular, okay? So anytime they call it a regular, let's see if I have a note of that in here. Yes, anytime they use the word regular, it means that our delta x is consistent for all of the rectangles, okay? All right, let's scroll back up. For my first rectangle here, I am using, think about where the height is coming from. The height is coming from the left corner. So for this particular one, it's going to be a left corner rectangle. So it's a left-handed rectangles. So the height for the first one is calculated by doing f of 2/5, right? Area of a rectangle, height times width, right? And the width is 2/5. For the second rectangle, the height is f of 2/4. No, it's not. 4/5. And the width is 2/5. For the third one, the height is f of 6/5, and the width is 2/5. For the fourth one, the height is f of 8/5, and the width is 2/5. And for the fifth one and last one, the height is calculated at f of 2, or 10/5, right? That's what created that rectangle, and the width is 2/5, okay? And the total area we want to add up, you see where sigma might come into play now, hopefully. We're going to add up all of these, okay? I certainly could factor out the 2/5, or I could just grab my calculator and start plugging in these values, okay? Well, I did that. I found all of these values with my calculator. If you want to pause the video for your notes and find these values with your calculator, that would be very helpful. I actually used the table function on my calculator to do that, so that I could find them kind of quickly. So let me just fill some in here. I actually lost it on my calculator. I cleared it accidentally. So negative x squared plus 5. All right. So here are my heights. 4.84. 2/5 is 0.4. 4.36 times 0.4. 3.56 times 0.4. 2.44 times 0.4, and 1 times 0.4. And then I am going to find the area of each rectangle for my 5 rectangles. So feel free to pause and do that as well. Here, I'm just programming it in my calculator quick to help me with this piece as well. This 1.936, 1.744, 1.424, 0.976, and 0.4. And remember, we're adding these all up. So now, total lower sum approximate area is, again, you feel free to pause and add these up. 6.48. Right, we are going to do this again, but this time we're going to do it with our upper or over, right? So this will be an over approximation. Again, we have 5 rectangles. Let's see if I can be a little bit smaller with my writing. First rectangle, height. Now, height is going to be calculated when x is 0. Next one, f of 2/5. The next rectangle's height is f of 4/5. So what can can I fit this last one in here? And then there's a 2/5 behind it. Oof. I switched to a Word doc and I can't go off the page now. That's a problem for me. 2, second one, third one, fourth one, fifth one. Grab my calculator. The kind of fun-ish neat thing is that most of these I already have. The first one's height is 5 times 0.4. This one I already have total. This is 1.936 if you look at that from before. This one is 1.744. This one 1.424, and this one is 0.976. So this time when I add them all up, let me add them all up here. Oof, 8.08. By the way, this one was a 2. Okay. So my area approximated with that overestimate is 8.08. Awesome. Excuse my cat playing here. This was my under, this was my over, and the actualized in the middle. Okay, I don't know about smack dab in the middle. That's a conversation for another day. It depends on the shape of the graph, okay, and the width of each rectangle. Okay. Excuse me. For this next one, it says find the upper and lower sums, so basically doing the same thing, of f of x equals x squared. I think for this one, I think I'm just going to not do it because it's really very similar problem. It's just that the parabola opens up and not down. So I'm going to skip this one for now. We can certainly discuss it. If you have questions on it or you want to see it worked out, come and see me or send me an email or something. But if we think about this though, 0 to 2, if I'm going to underestimate it, underestimating, we'd have to use the left corner. I think we say left-handed approximation, is this time if that's the under or the lower, right? If, where before, let's come up here 1 second, this one, our under estimate was using the right corner. This was a right. So it depends on the shape of the graph whether or not an underestimate is going to be a lower or an upper. And I will say, if your graph, ours are strictly, like this was strictly decreasing the whole time. If your graph is decreasing and then increasing, you will have some under, some over if you do a left-handed or a right-handed. So unless it's consistently decreasing or consistently increasing, you're not guaranteed over or under, okay? So, all right. This part of our notes is just saying that, hey, we can do lowers or uppers, or we can do lefts or rights, and they're not guaranteed to be consistent, okay? Something to note is if we wanted to talk about the accuracy of our areas, and if we wanted to make the area more accurate, right, I'm wanting to make our approximate more accurate, we would need more rectangles. So I'm going to grab this here, this video, open it up and show you, and I don't think it's a video, I think it's just kind of like a clip showing you what we can do, okay? Or maybe not here. Let's go. No, Janine. There. So the more rectangles, the less over and unders we have, right? The less undercounting and overcounting we're going to have. So if you're just over or undering by smaller amounts, you would get a more accurate area. In other words, we've talked a lot about limits in this course. So if the limit was taken as this, as the number of rectangles increased to infinity, we would have a better approximation. And I'll go one further than that and say, not only are we taking infinite rectangles, but we're also taking, because we have a definite interval we're working with here, it's 0 to 8, it looks like. But also consider this, the width of each rectangle is going to 0. So if we take the width of our rectangles and we take that limit as it approaches 0, we will have infinitely many rectangles, thus an accurate area under the curve. So something to think about. It's kind of neat. All right, let's get rid of that. And let's go here to example 5. Here it says just do a lower sum with 4 intervals. This is actually also too similar to that. So I don't think I'm going to do that one either. Let's go to something a little bit more challenging like number 6. First, I'm going to zoom in to the graph of sine, and I'm just going to show you a picture of it from 0 to pi over 2. So sine of 0 is 0. Sine of pi over 2, let's go here, is 1 right here. Okay. Sine of pi over 4 is root 2 over 2. But the graph technically does something like this. It's low, and then it swoops high, right? And actually, I need to rewind that just a little bit because we know it does something like this, and then it kind of does something like this. And somewhere around in the middle, it has a shift in concavity. And since we've already talked about concavity, you understand that. Okay. Ooh. Do I mean that for this graph? Let's take a peek. I don't think it's right there. I think it's right here is the shift. There we go. But we are only considering this graph from 0 to pi over 2. So I'm going to erase the stuff I don't want, which is that. Okay. All right. We're going to cut this into 6 subintervals. So I have a gap from pi over 2 to 0, and I'm just subtracting because if it was, say, 2 to 10, my gap would be 8. So subtract over 6 intervals would give me pi over 12. That is the width of the intervals. So this is going to be my delta x. Holy smokes. Okay. Now, that means, let's see, if I want to be consistent on here, this would be 6/12. 3/12 pi. One, 2, 3, 4, 5, 6. All right, something like that. Right. Yes, I could simplify. I understand. All right. Okay. So we want to do a lower sum. So for this one, since I want to do a lower sum, I would use the left corner. Okay. So a left sum. So my first rectangle. Oh man, this is going to take us a really long time. I don't think I'm going to do them all. I'm going to show you how to do a shortcut with sigma, and then we can use our calculator. Okay. But the first It's easy. It's nicer to transition to sigma notation. I could do I or I could do X. It doesn't matter. I'm starting with 1 and going to 6. That's 6 rectangles, okay? I'm going to try to do generically here so I can use my calculator. But first, my height for the first rectangle is f of 0, right? The height of my second rectangle is going to be f of pi over 12. The next one, f of 2 pi over 12. Right? And then the width for each one of these is pi over 12, pi over 12, pi over 12. And this pattern continues until I get to my sixth one, and it's f of, now be careful, my last one's height is not f of 6/12. My last one's height is below it. Make sense? So that one's going to be 5/12 pi, width of pi over 12. Okay, now how do I talk about this generically? Well, I would put here the function, right? I'll go like that for now, times the width, right? So height times width. Now I know my width, it's pi over 12. What I don't know is what I want to put in the box, right? I don't want to just put sine of x in there, because if I put a 1 in, I actually want it to calculate the height at 0, right? So this is when I'm plugging in a 1. When I'm plugging in a 2, I get pi over 12. When I plug in a 3, I have to get 2 pi over 12, so on and so forth. So starting at 0, and I'm increasing my input by pi over 12 each time. What does that look like? I need more space. Now, if we were doing a right one, we wouldn't have to monkey with this as much, okay? I like to say, well, here's where I'm starting, okay? For each I after that, I'm increasing it by pi over 12 amount. Now, if I put just an I here, I have a problem, because that means when I do my first one, I will be finding the height at pi over 12. Well, that's the second rectangle, actually, not the first one. So I need to back this up one like so. Now, some people would say, Janine, you don't need to have the 0 on there. You're right. But if it was going to say start at 3 pi over 4, I would need to have that included. So that's why I had a 0 there. Okay, so this is your f of x, and then your width. So your height is calculated this way. If you don't believe me, look at the picture and throw some x's in. Oh, I put I there and I put x there. Silly. I have to be consistent. And then I go to 6. Okay. Now, I'm going to grab my calculator and put this in. Notice these are in radians though, so be careful. Which means the area under the curve is approximately equal to this number. All right, so if you go in calculator, if you have an 84, you're going to go under math. Oh, I have an old calculator, it doesn't have it. Okay, so I'm going to pull up my calculator here. Math, oops, just math. looking towards the bottom, I see summation. And you can put I, you can put X, whatever your variable is, just make sure that the variable down there matches the variable there. Okay, so I'm starting with 1, ending with 6, and then what do I have in here? Sine. I have to be careful here. I'm going to do pi times the quantity, x minus 1, close that quantity, divided by 12, and that's all going into the sine function, okay? If you're kind of new to calculators and you're interested, the newer ones can do a fraction, alpha, and then the variable. So here I would have pi times the quantity, x minus 1 over 12. Okay, so that's just going in the sine function. Better close that. That's just going in the sine. And then after it is pi over 12. No. And actually, since pi over 12 is a constant, I don't even need it in the sigma. Let's like if you factored it out, it could be in front of it. Either way, too many parentheses. Open, close, open, close. There we go. 0.8633821. 0.86338. 86338. All right. Approximate area under the curve. Last thing for this section is to quickly discuss that we can also do a midpoint rule. So what the midpoint rule is if we don't have to find the height of the rectangles by going after the left corner or the right corner. We could go after any place in between there, including the middle, right? So it could be left, could be right, could be middle, could be anywhere in between there actually, because ultimately we're going to try to take the limit of this thing and have infinitely many rectangles. So anywhere in there we calculate the height, we'd be happy. However, we're going to do midpoint for this one. So here we have 0 to pi for the sine curve. Let's see. Down low, curve this way, and this way, and then this way. So here's where pi is. I'm going to go from 0 to pi. Okay. Now, I'm doing midpoint, and I want 4 rectangles. So, look something like that. Okay. So, this is pi over 4. This is pi over 2. This is 3 pi over 4. Okay. Now, if I'm going after the midpoint, my very first one, see if this makes sense to you, is going to be in between here. So here is where the height will be dictated for this rectangle. And then here is where the height will be dictated for that one. And then here for this one. And then here for this one. And notice now we have sum over sum unders, which is okay, right? And probably more accurate than strictly doing a left or strictly doing a right. Although, since there's symmetry here, we may have noticed some things. Okay. All right, so the middle here is pi over 8, 3 pi over 8, 5 pi over 8, 6, 7 pi over 8. Those are my mids, okay? Without using the sigma on our calculator, we would do, for the first one, the height is sine pi over 8 times, what is the width of the whole first rectangle, right? Well, remember the gap we're doing, so it's gap divided by how many rectangles is your delta x. Well, our gap is pi, so our width of each one of these is pi over 4. So height times width, height times width, height times width, height times width. Okay, now something to note here with midpoint. Remember how before I said if you wanted to do sigma, here we're doing 4, it's, f of x times the gap, right? All of these. So it's going to be sine of something times the gap, the width, right? Height times width for each one. All right. Okay. Usually, I like to figure out where the first one's going to be. And I'm going to add for each. So for 1, will end up being pi over 8. For each height after it, it looks like the gap is pi over 4. Well, of course it is, because it's one gap later, right? Even though they're offset. So I'm going to make this a little bit bigger. Each gap is 1/4 pi later. I don't want to do it for the first one. Does that make sense? And then, of course, pi over 4. And if you grab your calculator and you calculate this, you will get mine here. Math summation 1 to 4 sine. The first one I have is pi over 8. Okay, and then I'm adding to that pi over 4 x minus 1 time for each. Okay, let's see if I got this. I have pi over 8 plus the gap is pi over 4 to get to the next midpoint. I don't have to do it for the first one, but I need to do it for all the rest. So I like that. Every parenthesis that's opened is closed. Awesome. And then behind sine, we're going to go times the width of each rectangle, which is pi over 4. .05. There's my approximate area under the curve. Some of the rectangles are overs, some are unders. It's okay. Some of them have an over and an under. That concludes this section.